Welcome back to part 13 of our workshop. The last real thing we have to worry about to be able to implement any of the instructions in the instruction set is dealing with an address. We first run into addresses with SHLD and LHLD, but they're used often as well down here with our jumps, our calls. So we do need to know how to deal with addresses. The good news is dealing with addresses, we actually already know the logic for. Addresses are always 16 bits in size, and we already know how to process 16-bit immediates. But just for the sake of, I guess, clarity or ease of reading, I'm going to implement a separate address function, even though the logic is going to be the same as if we had a 16-bit immediate. I'm just going to do it anyway, just for clarity as we're going through all of these instructions. D16, I know to use an immediate. A16, I know to use an address. But if you want to, just claim that an address is a 16-bit immediate, fine. That works too. But I'm going to do it this way. So because the logic is more or less the same, I'm pretty much just going to copy it directly out of our immediate function. So it's the same idea. If our first character in our token is a digit or a $sign, it's a number. The other nice thing about addresses is every instruction that uses an address only ever has one argument, and that one argument is the address. So I can just go ahead and just know it's tokens.first if I'm dealing with an address. So if we have a number or a $sign, then we just got to do the same conversion that we did before, tokens.first. If the first character is a $sign, we just want to make sure to convert it as a hex number. And let me make sure I didn't make this. Yep. Let me just fix something right here real quick. Make sure it's base 16 if it's a hex number. So we'll say if it starts with a $sign, we want to convert the string to a short. But we don't want to convert the whole string to an unsigned short. We want to chop off that first character, that $sign. Otherwise, we don't need to chop off that first $sign. We still want it to be an unsigned short. But we do not need to chop off that $sign, and we want to make sure it converts to decimal rather than hexadecimal. Otherwise, it's going to be a label, and we're going to need that label to be processed. So let's go ahead and do that. Let's process the label. And it's going to be exactly the same as we did before. Just fix that right there. All right, same thing as we did before. So we're going to say if we're on our second pass, we're going to iterate through our symbol table. And if we have a match, then we must want the value of that label. And we can say we found it, and we can break out. If we get to the end and we did not find it, then we should throw an error. And then in all cases, we need to make sure that if we're in pass 2, we actually output the value that we have. And again, we make sure to remember that we are outputting in little endian format. So the way to do that is just take the bottom half first, and then we can add the top half after that. And that's it. Again, the logic for address and immediate, basically the same, but just for ease of as we're working through, right, you see a D, you do immediate, you see an A, you just automatically think address. At this point, you should be able to process all the moves, which we already did, all of the 2 register arithmetic instructions, which we already did. You should now be able to process all of the instructions in this top quadrant as well. And you should be able to process the vast majority of instructions in this bottom half. The only real exception left that we don't know how to process are these RSTs. And so we'll do that right now. There are 8 RST instructions named RST 0 through 7. If you were studying 8080 Z80 assembly, you would know that these are your reset vectors. We don't necessarily need to know that these are our reset vectors, although I do hope as you work through and as you implement all of these instructions, you are actually reading up to see what they are and what they do, and might be getting ideas of how you might be able to use them in your own future Z80 programs. But let's go ahead and actually do the RST together, since that's the last one that we actually don't yet fully know how to do. So the first RST instruction is at hex C7. So RST is going to be C7 plus some offset, right? And there's a number of possibilities, 0, 1, 2, 3, 4, 5, 6, and 7. So we'll say void RST is tokens, output, output. Again, we should be used to the boilerplate by now. We want to make sure that RST does have one and only one argument. So we want to make sure that first is not empty and second is empty. We then need to actually know what that offset is. So I'm just going to convert tokens.first, or the one argument we have, 0, 1, 2, 3, 4, 5, 6, or 7, into an integer. And we can check to make sure that offset is greater than or equal to 0 and less than or equal to 7. Because if it's for some reason not in that range, we have a problem. So if we are in the correct range, then the action we want to perform is tokens, output. All of our RSTs are only 1 byte in size. And then the formula is hex C7 plus 0, 1, 2, 3, 4, 5, 6, 7 times 8. Actually, pretty much exactly the same as the inners that we did before. Just we had the actual numbers instead of having to do the register to number conversion. But it's the same idea. They should be 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8 apart. So we should be able to say offset times 8 or bit shift by 3. Otherwise, we just want to error out. We want to throw a new exception, and we'll say invalid reset vector, I guess. And we'll print out what the invalid reset vector is. With that now complete, you should be able to go through the entire rest of this instruction set and just follow the formulas that we've been using to get to this point. And you should be able to implement every single instruction within the Intel 8080 instruction set. However, even when you get to that point and you are able to implement them all, we're still not quite done yet. There are a couple of pseudo instructions that I want us to implement, which will give us a bit of a richer environment so that we'll be able to do more and more powerful things with our assembler. But when you are done with all this, definitely give yourself a pat on the back. I would create a test program that actually tests every single one of these instructions to make sure that they are actually producing the correct hex numbers. But yeah, give yourself a pat on the back. We're almost home. So let's save our work. And I will say, well, I'm going to pretend that I did them all. So I'm going to say implemented all instructions. And I'll see you on the next episode, and we'll wrap up with a couple of pseudo instructions.